Hello everyone. So I hope I am audible. Can anyone tell me if I am audible or not?
Yes,
Okay. So I guess your course has been started. So can you guys see my screen? Yeah, you guys can see my screen, right? Yeah. So can one of you tell me like what all things have been covered in your week one? Just any one of you.
number system, binary,
Yeah.
and hexadecimal, and their conversion
Hmm.
to one another,
Okay.
and
Okay. So you guys haven't started the Boolean operations, right?
that is in week two.
Okay, fine, fine. So, okay, let's start with it. So, let's keep this session to interactive. So whenever someone wants to ask anything, you can either type in the chat box or just unmute yourself and you can ask your questions. So I guess professor has been teaching you the course, so most of the teaching part will be done from his side. And I am here to like take your questions regarding what all things you guys are either not understanding or you want to discuss more about. And some basic questions I have included in my this session so that we will have a good refresher in this course, whatever is going on. Okay, understood. Yeah, so let's start with it. Or else we can wait for some 5 minutes. Some people are still joining. Meanwhile, can you guys type in the chat box like which year you are in or which college you are in so that I can just have an idea. Anyone? Okay, fine. So we'll just begin with it. So, as the course outline is already known to you guys, that week one will be your introduction and number systems. So, as one of you guys, Avinash, updated me that you guys have covered till number system, convergence among themselves. So, I will start with what is digital signals and why do we use these circuits. So, instead of me presenting you guys, I would like to ask you while this slide is open. So, can any one of you like define what is digital signal and analog signal? Although I have written it, I would like to know your understanding beyond this. So, any one of you can unmute and tell. Yeah, Avinash.
Like signals are inherently analog in nature, like speech
Hmm.
signals are. So to convert it in processable by our systems like mobile or something, we'll need to convert it
Yeah.
to
Yes, exactly. So
digital.
the speech and the sounds that we hear, we talk about. So these all are your analog signals, and they might be having varying levels. So, like as we can see, yeah, as it is visible in this, as I have denoted here, the analog signal might be having some continuous values. So let's even consider a sinusoid wave. So a sine function, as you guys know, will be having a continuum of values from -1 to 1. So at a specific x, if you try to pinpoint it, it might be having a very precise value. So that is the thing about analog signals. Whereas the digital signals, they may be having a very specific levels to it. So at a specific time instant, or if you consider this as an x-axis, it will be having a very specific value. So here the square wave is shown. So till this point, this is having a value 1, and beyond this, it is having 0. So, and the other digits that you see under this, like 0, 0, 0, 1, 1, 1. So these are also binary, and they also have some step values, but they are 4-level signals. So if this square wave had a break in between, so that will be your 4-level signal. So as we can denote here, so let's suppose this was the thing. So this signal would be having a 4 level in it, so that will be your these kind of signals. Whereas the analog is this kind of thing. So why anyone else than Avinash? Why do you think we need these conversions in between analog and digital? Anyone? Anyone else than Avinash? So he's already participating. So I would like someone else to speak up. I hope you guys are receiving these messages in chat box. So you guys can type also if you want. If unmuting is not possible and don't want to speak up, you guys can still type. So the thing I asked was, why do we need to convert between analog and digital if like analog is a continuum of values, and if it is good enough, so why there is need to convert it into digital signal? Anyone? Okay, Mohan, you just joined. So we just have started. So I just took an update from one of you guys, like what is going on in the course. So week one, you have covered introduction until introduction of the number systems and convergence between them. So this is a session in which you guys can discuss things with me, like whatever is the difficulty that you're facing in this course. And I have prepared some slides from my end, which I hope that it covers your week one studies. And we were just discussing what is analog signal and what is digital signal, and why do we need to convert in between them. So Avinash here answered that what is analog signal, so and what is digital signal. So analog will be having a continuum of values, whereas digital will be having a step kind of values. So here I drew these 4 levels to denote these other numbers that are shown under this digital signal. So I just wanted to know from one of you, why do we need this convergence? So I hope that professor has covered it in the introduction. So if any one of you can contribute, that will be very nice. No one? Fine. So analog signals, usually, as Avinash pointed out, it is the speech or the sound that we hear. So as a signal, here in this slide, I have mentioned that digital signals are affected lesser by noise. So noise is a kind of signal that you can see here in the bottom right part. So this is a signal A, which is a clean sinusoid. That is similar to what is denoting in this graph, whereas the signal B below it is denoting a signal that is affected by a noise. So this can be like any kind of noise. So when you keep on as you go on studying different subjects from now on, so in one of them you will study what is noise and what are its characteristics. So noise will basically degrade these signals. So these kind of degradations are inherent in nature. So for an example, if you try to speak someone just beside you, you will be able to listen and speak very clearly. But you all guys use mobile phones. So if you are trying to talk to someone else, you are using a mobile phone and not trying to shout all the way, right? So there this things comes in that there are noise sources in this nature, so which will prohibit these analog signals to travel very far. So like you guys watch television or even talk on phones. So there this voice is made possible because of these conversions. So your analog signal, that is your voice, is converted to in a digital format, and that is then transmitted over the networks. So and why do we use digital signal? Because those are affected less by the noise. So if you just with some attention see this signal, so this A is having a continuum of values, whereas this B is having a continuum of values, but it is affected by these noise points. So like if you try to superimpose that noise on your digital signal, so what you would get is there will be still some noise, but overall this level will be still very high as compared to the level which is down below. What that would mean is that whatever thing that is at the receiving end would still see the majority of signal as this to be 1, and the other would see it to be 0. So just for an example, this long range communication, so that is made possible by these analog to digital conversions. And that is one of the application, like why do we need to convert between analog to digital. So overall there is no better signal among analog and digital, but rather a combination of both is used. So, as I pointed out in this example, that we use mobile phones for communications. So that is one example where analog to digital conversion is done. Can one of you type in the chat box? Not one of you. You can attempt. So just tell me any other system, like communication system, you can use which uses analog to digital signal. There are lots of examples around, so you can point out any one of them. So either you can unmute and tell, or you can type in the chat box. That is fine. Mobile phone, yeah, correct. That is true. Microphone, yeah. So, yeah, still we will consider it as a part of larger system that is mobiles. Digital clocks, yeah, correct. So, yeah, that was Avinash. Yeah, so Avinash, can you tell me like both type of clocks will show time, but what's the difference between analog and a digital clock? Avinash?
Uh, that 60 seconds in that 1 second delay in digital systems is
Hmm.
generated by means of like conversion.
Okay. Yeah, you are going right. So, still you want to add up? Okay, okay. So let me add to your answer. So what happens is time as we know it can be defined in a very precise way also. So where is the pen? Yeah. So time, as you know, in our digital watch, let's say something can be shown as 0503 a.m. or p.m. Let's say. But as you know, the seconds can also be like in continuum in nature. So this digital clock can still show a very precise amount of seconds also. But can would we call this to be digital or analog? would still be this be a digital signal or an analog signal? If I use a digital watch that is showing this kind of time. Avinash, you want to speak up, or there is a lot of noise coming up? Okay, so this kind of signal would be still digital, but yeah, we have to define till what fraction or what decimal place we need to denote the time. So time itself is analog, but when we try to denote it or use a system to show it, that will convert it into a digital signal. So this will still be a digital signal if we just keep it to this place. But in actual, this can be even more precise. So this is it. So analog to digital conversion would require you to define some limit till which where you want to precisely denote your numbers. So moving on. So one more thing, why do we need digital signals when analog are so continuum in nature and so perfect? So here I have used this cartoon to show these two things. So let's suppose this left computer is your analog computer that is having information stored in an analog domain, and it is using analog signals to communicate. And whereas the right side computer is having signals stored in digital domain and trying to communicate in digital signals. So what would happen is if communication needs to be done, it has to be to and fro communication, right? So this computer has to speak up, this has to process and listen, and then reply back, and then further process will go on for a successful communication to happen. So in this case, as you see, the left side computer, where you haven't defined precision to which this will try to process the data, so it will just try to keep on processing this data point, and it will just try to figure out what to speak to the other computer. But this computer can readily listen, and it has a limit to where the precise points to take. So it can listen and transmit very fast, but whereas as you increase the precision, this computer will keep on struggling to reply back and communicate. So this is just a small example to denote why digital signals are needed. So information storage processing, it's more easier, faster and deterministic with your digital signals as compared to analog. But again, some applications do require only analog signals to be there for it to be just better. So as you see here, a cartoon at the left side of your screen, this is a gramophone. So how many of you guys know gramophone? I hope not many of you would know. So this will just use a vinyl record to play music. So this music is physically written or engraved on this vinyl sheet, and there is a needle in this gramophone which will just convert these roughnesses into sound, and that is actually analog kind of music. And that when we listen, so our ear would receive it and your brain will still process the analog signal quite fast. So there's a difference in which your human brain would work and the compute and the CPU would work. So there is a limitation of resources to CPU, and also there are many parallel tasks that a computer might be doing, but same is not the case with a human brain. So it would like this music better instead of hearing 0 1 0 1 and these things. But again, if you have kept up, these music signals can also be converted to digital these days. So there are something known as analog to digital and digital to analog converters, which would still accomplish this task. And more of the things are going towards a digital way now, because ultimately you have to use some computer to store and process. So coming to number systems, so I have denoted the number systems already here. So I would like to know whether uh, are these number systems familiar to you guys? So you can just type in this chat box. So what all bases do you know in which number systems would work? So I have just put a basic notation of how a number should be, not should be, must be denoted. So in bracket here you have the numbers that might be having some of these digits or characters to represent a specific information, whereas this subscript base would be the one of these numbers. So if you are working in binary, there will be 2. If you are working in octal, there will be 8 written here. Similarly for decimal and hexadecimal. So I would like to know from you guys, are the new number systems possible? Like, can you define a number system with base 7 or let's say base 20? Is it possible? Okay, Tanushri has said yes. Raghav maybe. Fine. Jyoti, yeah. Okay. Navya, okay. Okay, Divya. Are only girls joining this course or boys don't want to participate? Where is Avinash? Do you want to pitch in? Can new number systems be defined? Okay, so we'll just move on. So yes, new number systems can be defined, but these number systems are to be bounded by some rules. So like you can see, if you have a base 2, at that time you will be having only 2 characters. If you are having a base 8, this will be having a total of 8 characters. So here we start this with 0, 1, 2, 3, 4, 5, and 6 and 7. So if let's, for an example, if we try to define a number system with base 7, let's just assume, okay, for simplicity we'll go with base 3. So during that time, the digits that we will be having, this can be 0, 1, 2, and most of the numbers have to be defined in this only. And so the professor might have taught you to how to convert from decimal to different number systems. Yes or no?
Yes, yes.
Yeah. So let's do a short question. So let's convert 12 to base 3. So let's suppose we are using, so 12 is in decimal. So I will anyways solve this. Do you guys want to put the answer in for this? So I will just wait for 5 minutes. So since professor has already taught you how to convert from decimal to any new base, so I would ask you guys to convert 12 decimal to base 3 number and tell me what will be its value in base 3. Four zero. Okay, we have one answer. Sorry, why? You don't need to be sorry, man. That's fine. Yes, I will again reiterate. I am not your professor, and I am also student like you only, but I am just pursuing PhD. So you guys can be free with me. No need to say sorry and all. That's fine. 110. Okay. 777 by Raghav. Okay, Raghav. So what made you guess 777? Did you guess it or solve it? Okay, guessed. Fine, fine. That's fine. Okay, okay, fine, fine. Okay, so I think let's solve this thing. So we have a number 12 in base 10 that we need to convert to something. It will come up in base 3. So the usual way of conversion that you might be aware, if you have attended the lectures carefully, is that you have to select this base and go on dividing your number, and you have to write down the remainder, and that will form your new number in this new base. So if you do, if you see here, 12 can be divided using 3 if you multiply it by 4. So this will give out the remainder to be 0. And again, if this remaining number you have to divide, so this is just a formal step, but you can finish it here also. So just a sec. Yeah, so if you do this, so this gets divided and you get a 0. And then you have to divide this one also. So this will give you 3 ones, and this will still give you 1. And when you still divide this will be 0 and this will be 1. So you have to write it like this. So if you try to convert from this to base 3, you will get this to be your number, that will denote 12 in this our new number system. Yeah, correct, Ravi. Yeah, so pretty many of you just got the correct answer. So yeah, it's good that you are following the lectures. That's nice. Yeah, so as we were discussing earlier, why do we need these number systems in the first place? So that I have pretty much told you in the initial slides. So do you guys need to take a guess? Do you want to take a guess? Why do we need to use these number systems? Why can we not just use the decimal number systems? You can either type in or unmute and tell yourself. The
So
answer is
because
already, I think. Yeah.
computer do not know the human language, so they convert so they created zeros and ones
Hmm.
according to our language, and it will convert itself and deliver to us.
Okay. So actually, computer would know that counting also. But the thing is, if you know how computers work, so if you see in this slide, so we have this levels of information, right? So let's denote this to be by 1 1, 1 0, 0 1, and 0 0. So this is still binary, but this is 4 levels. So computer can like process in bits, if you're aware. So bits is something that we denote in binary, and binary system is again base 2. So this is something that we chose early on while developing computers. So do you guys know 8080? Like, are you aware of the 8080 processor?
8085.
8085, yeah. So has anyone worked with 8085? I hope like you guys would have known something about this processor. Okay, so why I'm asking that, because in if you do programming in 8085 computers, microcomputer, there the addresses that you put, that would be hex codes. So there the addressing of the memory is done using hexadecimal numbers. So there, that is one instance where you use hex codes to denote something for this computer. So other than binary, these codes were possible, but it was used in early on computers. But now these days, as you know, most of the things have shifted to binary. And why binary is considered to be safe? Because it has only two levels, and as we discussed, that noise can corrupt these signals. So binary levels will be least corrupted. So that is one reason why we use binary computers and binary number system for computers. So yeah, we have covered that. We can define a new base easily. And as this was the part where I hope you guys had finished this week, that number systems are interchangeable. So bases can be converted among each other, and as we have seen in previous problem, we converted a base 10 number to base 3 number. Now that base 3 is not that much defined, and it would definitely not be used. But we know how to convert these things. And again, as I have asked earlier, whether can we use a new number systems? Yeah, that we can use, but algebra for that has to be known. Now, by algebra, what I mean is you should know what the addition, subtraction, or different operations that you would do on this number system would result into a number that is still in the same system. So you need to know these operations very properly to perform the operations correctly. So this bit scary looking thing is what we did earlier. This is this just denotes a number. So has professor covered this floating point, this decimal point in lectures? You can type in either yes or no. Okay, that's good. So yeah, this is a decimal point after which the formula for conversion might change a bit. So this still remains in powers, but that changes a bit if you encounter a decimal. So this very big looking formula that we earlier used. So in last example, we got a number 110 in base 3. So there we don't have a decimal, but just we can test out this formula whether this really works or not. Yeah, so we had these digits. So according to this formula, we will just have to assume that there is a decimal here to accomplish what this formula tells. So if you are going left side to this decimal point, you have to multiply um, this place by the number of steps it is away from the decimal point. So this is something that is known as place value. So you need to know what is the place value of a specific number. So here in this case, f lies one step next to this decimal. So this counting usually starts from 0. So left to the decimal, this will be place 0, this will be place 1, this will be place 2, 3, 4, 5, on and onwards. So any it is Adi Manush. Okay. And to the right of this decimal, we denote this by minus 1, minus 2, minus 3, and so on. So this formula now becomes a bit more sensible that this a lies at fifth position. So we use this base n and its power 5. So this conversion from base n to decimal would involve this thing. So we can just test out whatever we converted. Okay, Tanushri is quite fast. That's good. So this will be 1 into 3, 0, 1, 2 to the power 2. Then this will be 1 into 3 to the power 1 plus 0 into 3 to power 0. And since we don't have a point after this, so this will just come out to be 12. And this is the point where we started our decimal to base 3 conversion, and now we converted it back. So this came out to be 12 in decimal. So that again cross checks that our earlier conversion was good enough. So just for an example, can you guys convert this number to decimal to base 10? So I will just wait for some 5 minutes and let's see. Why is binary less corrupted? Is it due to larger difference in voltage maintained between levels? Okay, meanwhile you guys are solving, Avinash has put up a question that why is binary less corrupted? Is it due to large difference in voltage maintained between levels? So yeah, by and large that is very true observation. So what happens is, I have told you guys what is noise, but let's say if this is your noise signal, so this is from minus 1 to 1. Now this is a very good looking noise, but noise is usually not like this. But just for example, I'm saying that this is the noise which is corrupting your binary levels. So this binary level, let's say, lies at 1 and this lies at minus 1. So if you just add this signal to this would reach to from minus 2 to 2. So at the highest point where the value is 1 and here where it is 1, it will reach 2. And this will just show up like this. And if your computer just understands values between -1 to +1, you would still need to down convert it so that this lies in voltage levels that is understood by your computer. So by and large, this noise will take over to your original signal. So now if your computer tries to process something at this time instant or at this time instant, so this will be something that is very less than what is 1. So yeah, this depends on the tolerance levels that your computer might be able to understand. So if this is your signal which your computer is going to process, this is very well separated from these two levels in voltage domain. So this is separated by 2 volts. But if your noise just overtakes whatever your signal is, your computer will not understand what you are trying to store or process. So yeah, if you are having noise that is having comparable levels to your original signal, then you will face a lot of problem while storing or processing this data. So as I mentioned here, if there are 4 levels, so if this kind of noise, which is -1 to +1 sinusoid, affects this level, this will just change the information. So your computer would never understand what you wanted to say. Okay, so we have one answer from Divya, that is 12.148. Has anyone else tried to solve it? 13.037. Okay, Pradeep. Now let me tell you, in this base where we are using 3, you'll encounter these powers, the inverse powers. So you can keep the answer precise to 3 or 4 decimal points. Okay, so let's solve this thing. So if you see at this formula, we have some powers that will be associated with our base 3. So I'll just use this part. So this 110, we already defined it according to its place value at top. So I will directly use that. So it will be 1, and let me write down the place values. So this will be 0, this will be 1, this will be second, this will be -1, -2, and -3. So if we simply use these place values, then this will be 1 into 3 squared plus 1 into 3 to power 1 plus 0 into 3 to power 0. Fine. Now we have encountered the decimal point. Now the powers will flip. So it will be an inverted thing. So this will be 0 into 3 to power -1 plus 1 into 3 to power -2 plus 1 into 3 to power -3. So if you just simply look at it, this will be, so this 12 I will directly write in decimals, and after the decimal point whatever comes, that we'll put here, and let me put that in this bracket. So this will be 0 upon 3 plus 1 upon 3 squared plus 1 upon 3 to power 3. So if you try to solve it, this will be 0 plus 1 by 9 plus 1 by 27. And okay, I will have to use a calculator. So this will give out to be 12.148. This is precise up to these 3 points. So as you see that this division is not complete, as these are the powers of 3 and it doesn't completely divide 1. So you would still have this 148 to be repeating in nature. So from mathematics notation, as I remember, you can denote the repeating decimal fraction to be like this. Yeah, so in base 10, our number 110.011 would convert to 12.148 to the base 10. I hope you guys got this question. Yeah, Avinash, you are also right. Pradeep, yeah, just revise how we convert this. I hope you also got it. So Did you get it, Pradeep? How
Yes, sir.
we did the conversion? Yeah.
Yes, yes, sir. I missed that one, sir. Sorry.
Which one?
After the decimal point, the second number.
Okay, okay, okay,
I
fine,
just
fine.
made it as zero. So only I
Okay,
got the wrong.
okay, fine. But you got it. How to do it, right?
Ah, yes, sir.
Yeah, yeah. So like, take your time. It's fine. You can also ask me if there is some issue while doing conversion. This is pretty straightforward, so I hope you get it. So now moving forward, now that this was something that we converted from your decimal to some n-based system, and from n-based system to back to decimal. Now other popular number systems would be octal, binary, and hexadecimal. So binary is already very popular. So if you try to interconvert between these systems, so I hope the professor has told you there is a shortcut kind of thing. So do you guys know that? Yes or no? Guys? Yeah, okay. Fine. So I hope professor has told you that directly. So here that is the same thing that I have written down and tried to explain here. So here now why that is possible only between binary, hexadecimal, and octal. And do you guys know that? You guys can tell me why is this direct conversion possible only between binary, octal, and hexadecimal? And also let me add to that question, which will be the next base that will be having a direct conversion with binary? This will be pretty interesting to know. So just write down the next base that will be having a direct conversion to binary. You can type in the chat box. 32. Okay. Yeah, so this is also pretty straightforward if you look at this slide. So any number system which is having a base of 2 to power n, that will be having a direct conversion to the base 2, that is binary. So even if you use a base n equal to 4, that will be directly having a conversion to your binary base. So in case of octal, groups of 3 form. In case of hexadecimal, group of 4 forms. And in case of if you are having a base 4, that will be group of 2. So yeah, and further on, if you take 32 as Jyoti told, you will have to group these digits in groups of 5 to get the direct conversions. So this is just an example. So we will try to solve some problems before we run out of the time. Yes, so I hope the introduction part was it was already well taught by professor. So I have some questions, not many more for you guys. We already solved some during the slides. So which of these laws suggest that tools for semiconductor manufacturing will double every 4 year cost for the tools? So which one of these laws told that? So you can type in the chat box. Okay, Santosh says Moore's law. Tanushree also says Moore's law. Read the question well. Jyoti says Rock's law. Prajwal also says Rock's law. Yeah, so the answer to this question is Rock's law. So what Moore's law tells is the density of semiconductor will double every 2 years, I hope. Uh, so this was a law that was like corrected some time ago. So that is denoted by Moore's law. So density rule is given by Moore's law. Macheron's law tells that whatever system you would like, that would cost you around $5,000. I hope this is the right figure. So is this true? So in every 18 months, yeah, Tanushree, that was the correction. That's true. Now Macheron's law says that your favorite computer that you want currently would cost $5,000. Is this true? So I want you guys to type in your favorite laptop or system and its price. Let's check the applicability of Macheron's law. Meanwhile, Rock's law is the correct answer. So semiconductor tools is something that you require to manufacture semiconductors. So tools would mean the fabs plus the design softwares and required expertise. So these all things come under semiconductor manufacturing tools. So nobody likes a laptop or system. I guess Mashroon was wrong then. Moving on. So yeah, you can type an answer for this question. So what is dynamic range in a digital signal? So whether it's maximum noise which cannot affect the signal, or is it precision of the information that we can denote using the number system in a digital signal? Is it maximum and minimum distinguishable signal that is over noise floor, or is it the amount of memory needed to be stored for this signal? So you guys didn't tell me your favorite laptops, so you can tell me answer for this question. Avinash says C, maximum minimum distinguishable over noise. Pradeep also goes with C. Ravi also says C. Okay, so pretty much everybody is correct. So the thing that we saw in the earliest point, and also the thing that Avinash asked, whether the difference of voltage levels makes binary to be the most used number system. So that is true. So in binary, you have two levels that are spread wide apart. So this difference of these voltage levels, voltage A and voltage B, and let's suppose if you have a noise floor like this, so this amplitude of this noise is not going to affect your minimum signal to the amount that it will be distinguishable. It won't be distinguishable from your VA. So the amplitude of noise has to be very less than the signal that you're actually using. So so dynamic range is defined by this. Yeah, now we already know how to convert between hexadecimal to then binary and then binary to octal. Why don't we try to solve this question? So you guys want to give it a try? I hope this is a pretty straightforward question for you all now. Still I'm waiting and parallelly I'm solving it. So I'm hoping before I complete the solution, you guys will type in your answers. So we will start with what we have. So we have 1E.43 in base 16, and that will be something in base 8. And we know that these bases which are in powers of 2, so this is 2 to the power 4 base 16. This we can convert to binary base, and that we can again convert quickly to the base 8. So base 8 is 2 to the power 3. So we will use this thing directly. So if you convert 1 to binary, so you will require 4 digits. So this will be 0001. E is given by 1110. 4 4 will be given by 0100, and 3 will be given by 0011, and there was a decimal in between. So Jyoti has typed in one answer. I guess she would be right. So this will convert out to be 0001, 1110.0100 and 0011 to the base binary. Now we know the rule of conversion from binary to octal. We need to group these things, but as I have told, always start from the decimal. So if you start from decimal, let's go to left first. We will group this in groups of 3, and this group remains incomplete, so we will just use one more 0 to fill it up. The 0 won't add anything. Now if we go to the right, to the decimal point, let's group this. Here we need to add one more 0 to make it a complete group. Now if we convert this to octal, this will be still 0. 0, 1, 1 would become 3. 1, 1, 0 would become 6. And we have a decimal. Then 0, 1, 0 would become 2. 0, 0, 0 would become 0. And the last one, 1, 1, 0 would become 6. Now if we write this down, this will be 36.206 to the base 8. Yeah, so someone has answered, I think. So yeah, pretty much everybody were able to convert this. That is very good. Ravi, yeah, that's true. So the answer to this question is B. And this direct conversion you can use to save some time. So even if you encounter a number system like that is, let's say if someone gives you a base 100, then you can just directly down convert and up convert between base 10 and 100. So those are the things that you can keep in mind. Usually people don't ask in those bases because those are not very popular. Now moving on. So you guys have dealt with addition or what? You can either type in or tell me by unmuting. Rajbal, yeah, B was the correct answer. Okay, you are answering for this one or what? So yeah, first tell me whether you guys know binary addition or not. I guess you guys know from the responses. So yeah, still I will go through this. So here before going on for addition operation in binary system, you need to know some basic addition. So between two, so since in base 2 you only have two digits, either 0 or 1. So you need to know all the permutation and combination of the additions that are possible. So I'll just write it down quickly. So 0 plus 0 will give 0, 0 plus 1 will give 1, 1 plus 0 would give 1, whereas 1 plus 1 will give 1 0, where you have to keep the 0 and C goes to this 1 goes to carry. So just quickly I will do it because I think you guys already know it, and this will become boring if I teach you something that you know. I will write carry here. So yeah, we will start with this. So 1 plus 1 will give you 0, 1 you have to carry. Again 1 plus 1, you have to write 0 and carry 1. Now this becomes 1 plus 0. This is again 1 plus 0. This one is 0 plus 1. And this is 1 plus 0. So this is the answer that you get. So yeah, even before you guys could answer that whether you know this or not, you guys already answered it. That's pretty sick. Yeah, now I think this is the final question. So we have already discussed about analog and digital quantities. So I would like to know from you guys whether temperature variation is an analog quantity or digital quantity. So you can either unmute and tell, or you can just type in chat box. While you are typing in your answers, I would say um, give your assumption. So is this always the case that whether, while temperature will always be analog? Analog, okay, Ravi. What about digital thermometers? I would like to know from you guys. The temperature variation shown on digital thermometer, whether it will be analog or digital. Yeah, I'm waiting. In nature, nothing is digital. Okay, Santosh has written something like a quote given by a well-known person, but that is true. So a temperature variation that will be always analog, but let's if you are using a digital thermometer, so that will again, as we have discussed, if something involves computers, there you need to perform the analog to digital conversion. Okay, my writing is very bad, I see. So if you convert your temperature to digital using this digital thermometer, so at that point of time it will be a digital signal. But yeah, over and wide, this temperature variation will always be analog in nature. But we need to convert it because we need to process it. And you just cannot go on telling that yeah, today's temperature is 23.4627 and so on. So that scenario will pop up that happened with the computer on the left. So you just keep on thinking and you will never be able to tell temperature to other person. So I hope you guys learned something and I hope that this was adding up to the lectures that professor has already taught. And feel free to like ask me some questions if you have regarding these lectures. So I will try to write them down, and if something requires time, I will come with some answers for your queries. So I will wait for some time, for some 5 to 10 minutes. You can discuss things with me, or you can type in, and I will see to it. Also, my mail ID is mentioned here, so you can put on your mails on this ID if you have any questions. You can write that down. Okay, everybody is living like that only. You can at least give me suggestions that you would require discussion more or problems more from now onwards. More problems. Okay, Santosh, noted. So since this was only your introductory week, so that's what. The difference between crystal and atomic clocks, if I could ask. Yeah, you can definitely ask. Yeah, so as far as I know, in watches, mostly this quartz crystal is used to maintain the timing. So that is more cheaply available. So if atomic clock is considered, this I think cesium 133 is used. So there this timing is given by the time scale that the electron jump occurs between its levels. So that is always a specific kind of thing and that gives a more precise timing. But crystal we use because you cannot ensure a pure cesium 133 everywhere. So where very precise thing is required, there people use analog this atomic clocks. That is mostly always giving the standard SI unit of time is defined by that only. But crystal is used because that is precise enough for our applications. So the crystal also gives out time based on its oscillation frequency. Problems. Okay, Ravi. I will try to include problems now onwards. So your main part will start from now onwards when you try to make out some logic of out of these number systems. So at that time, I think we will be having very interesting problems to solve. Okay, Prajwal, thanks to you too for joining. Hey, you guys don't need to call me sir. That is fine. You can call me Utpresh directly. So I hope nobody has more queries, so I think we'll conclude this session. Yeah, see you all next week.
Thank you, sir.